we are good to go. Oh, camera's still booting.
Well, this is going to be awkward. Nobody in the classroom. How many folks online?
Well, let's see here, we've got 10. 10 actual people.
Out of a class of 35, that's not. Sorry.
That's not much better.
Okay, folks, it's time to start. This is a first for the semester. We don't have anybody in the classroom, so everybody's online. Like to continue our discussion of quantum mechanics and all the really weird and cool things that we've figured out this last century. Just to recap a few things, Einstein pretty much convinced everybody, and we believe this still, that light, an excellent model for light, is that it's made up of particles we call photons. And the energy of those photons is basically equal to Planck's constant times the frequency of the light. And de Broglie kind of turned that around and thought of, well, if light, something we have always thought to be a wave, behaves like a particle, maybe particles have wave-like behavior. And that actually provided some incredibly convenient explanations for what we were seeing with atomic spectra and the current models then of the atom. And that really got a lot of attention very, very quickly. But his proposal is pretty much using the same math to describe particles that we use to describe waves, in that we think of light as carrying momentum just like a particle does. And so if we kind of do the math and said, okay, if we have the same relationship between momentum and wavelength that we do with light, that we have with particles, that would imply that particles have a wavelength given by Planck's constant divided by the momentum. And this actually helped explain atomic spectra quite nicely. And so if something has a lot of momentum, either moving very fast or has a lot of mass, well, it's going to have a smaller wavelength. And the thing about waves is, if the wavelength is really, really small, the thing, whatever we're describing, starts to behave more particle-like and less wave-like. And remember that we can think of the energy of a particle, its kinetic energy, as being 1/2 mv squared. And as I mentioned much earlier this semester, we can write this in terms of just the momentum, in that 1/2 mv squared is the same thing as the momentum squared divided by twice the mass. And so we can see that if something has a lot of energy, well, it's also going to have a lot of momentum. And so a particle that has a lot of energy is going to have a shorter wavelength. And so that's also kind of an analogy to light. The higher energy light has the shorter wavelengths and the higher frequencies. Now, how do we describe a particle as a wave? Something that has at least some localization, that we can talk about it being found in a region of space, but also having wave-like behavior. Well, in a classical wave, the amplitude of the wave, basically how big the wiggles, is a measure of, well, the probability of that wave interacting with something. And so what was done is to think of a particle as being a localized wave, where it's got a wavelength, and we can talk about it having, an amplitude of that wave, but having that amplitude restricted so that it's only large in a region where the particle is. So this is called a wave packet. And this is how we think of particles, at least in terms of what we call their wave function. And Heisenberg and Schrodinger were a couple of physicists that really made great advances in this, applying the mechanics, the mathematics we apply to waves, applying those to particles and seeing what would result. And taking de Broglie's idea and the idea of a localized particle, we'll find out, actually we'll talk about more of this in chapter 32, but Schrodinger developed a model of the atom that was far more precise than what Bohr had proposed by applying this mathematics of waves to particles. And the result of this math is that, well, we can think of the location of the particle being not precisely determinable, but at least we can predict the probability. In that instead of thinking of a particle always having this very precise location, we can only talk about the likelihood of it being measured in a certain region of space. So one result of applying this mathematics of waves to particles is that we cannot predict in advance the exact results of any experiment, whether it be the energy of the system, the location of a particle, the time of an event. None of that can be predicted in advance exactly. But we can predict to an incredibly high degree of precision the probability of a measurement resulting in a certain value. And the precision to which we can predict this probability, in fact, is extreme. And that kind of leads to a lot of philosophical questions. In what are we doing when we make a measurement? Do we actually alter reality when we make a measurement? Are there, in fact, multiple realities that we don't know which one will be in until we make a measurement or make an observation? This is all incredibly fascinating philosophical stuff that I wish we had more time to get into. But the result is that, and this is how Heisenberg and a lot of other folks started thinking about the problem, is that mathematically, if we describe something as a wave, it turns out that what is important and what we can focus on and what we can measure are probabilities. And one way of thinking about it, and this is how a lot of scientists think about it nowadays, is that it's not really wave behavior we're seeing. We're seeing a manifestation of the probabilistic nature of matter and energy. And that if you find that you can only talk about probabilities of something occurring, and you have, that means simplistically, if you've had any statistics, you can think of the likelihood of something happening if it's a random event following what's called a bell curve or a normal curve. Basically, it's less likely in some regions, more likely in others, and then less likely. So you have a well-defined mean and then a well-defined standard deviation. And so for like the wave packet, we can think of the envelope as being like a Gaussian distribution. So it's more likely to make a measurement of the particle being found, say, here where the amplitude is higher. In fact, the square of the amplitude of the wave mathematically gives us the probability of where the particle is. And then you can think of a standard deviation associated with that Gaussian distribution, that bell curve. And think of this as like a range of possible values of, say, position in this example. And basically what the math tells us, and this is a Heisenberg's uncertainty principle, is that if you have a product of the uncertainty, basically the range in the momentum values you can measure, multiplied by the uncertainty in position, that's got to always be greater than Planck's constant divided by 2 pi. That's what the math tells us. And the book uses a symbol h bar, a little bit of a, like a crossing a T through the H, to denote h divided by 2 pi. Because this factor of Planck's constant divided by 2 pi shows up over and over and over again. And so it's convenient to signify it with its own symbol. So the book uses a symbol h bar over 2. And because we have this linkage between momentum and energy, we can also talk about uncertainty in energy times uncertainty in time, always having to be greater than this Planck's constant. Meaning if we have a certain uncertainty in anything that we can measure, that puts a limit on how precisely we can make a corresponding measurement. In fact, thinking in terms, this is how scientists think of it nowadays, thinking in terms of momentum and position, basically position in one direction and momentum in that same direction, as being separate quantities really is not the best way to think about it, because the two quantities are always linked. The more we know about one, the less we know about the other. One way of thinking about this is considering a wave packet, just graphically. If we know very, very well where a particle is, that means this wave packet's going to be really, really narrow. A Gaussian distribution with a very small standard deviation. The delta x is going to be very, very small. But then if we look at the waves inside the packet, we don't get a very good idea of the wavelength. In fact, we get very little, we can't count, okay, the distance between the humps is this much over this many humps. But if the packet is narrow, we only might have a half of a hump inside our wave packet. It makes it very, very hard, in fact, almost impossible to get an estimate of that wavelength, the smaller that packet is. And that wavelength is what determines the momentum. If we don't have a good idea of what that wavelength is, we don't have a good idea of what the momentum is. You know, from de Broglie's wave relationship. And we can look at it the other way. Say if our wave packet is very, very broad, we really have less idea of where the particle is. So inside our wave packet, we're going to have lots and lots of wiggles. And to be able to get a really good average for what the wavelength is, or a more precise measurement of what the wavelength is. And so there's less uncertainty in the wavelength and the momentum. So just considering this model of thinking of a particle in terms of a wave packet, you can see that this sort of relationship comes out. And similarly, the more precisely we know the energy, well, the less we can tell about when it might have that energy. And the more we know about the timing of an event, the less we can tell about what energy was involved in that event. So if we can very, very precisely determine when a particle interacted with something, we have a lot less information on what energy that particle had. So these are all coupled. And you can see that in the relationship that we have between energy and momentum in an expression like that, at least for a free particle moving. So this really is a whole can of worms philosophically. And it turns out that probability is what's the important factor. It's what we can measure, it's what we can predict. And quantum mechanics gives us an immensely powerful tool so that we can predict these probabilities to an incredibly high degree of precision. Which means that if we were to repeat an experiment over and over and over again, we would get a very, we could predict very, very precisely the average of those measurements. And this kind of also answers the question of how can we possibly get an interference pattern by sending particles through slits. The idea that we can get a diffraction pattern and an interference pattern from particles, which if they have wave-like nature, we should be able to see. In fact, we have seen this. And if you send electrons one at a time, zinging towards a couple of very, very thin slits so that the separation of those slits and the width of those slits is on the order of the wavelength of that electron, because that's when we start to see interference and diffraction patterns with light, when the slits and their separation start to become on the order of a wavelength. Well, we won't get that particle ending up precisely opposite the slits. We'll find that it will hit a screen and be detected at possibly large angles. And if we send electrons through over and over and over again, one at a time, we'll find that we'll have more of them, say in a spot like around here on the screen, and then not very much, and then more about here on the screen, not much, and then more here, basically forming what we would think of as an interference pattern of intensity, basically number of impacts per area on any certain part of that screen. So that for any one electron, we can't predict where it's going to go, but we can predict the probability of where it's going to go, and that will form an interference pattern. And one of the key things about all this wave mechanics is that if you start superimposing probability distributions, like the Gaussian distribution, if any of you have had any sort of math where you've seen Euler's relationships, you know that sines and cosines, what we normally think of as waves, are just superpositions of the exponential functions that give us the Gaussian distributions. So that might be a bit more math than what you've seen, but for those of you who have seen that, once you start adding probabilities together, the mathematical result are sine and cosine functions, basically wave functions. So you can think of this wave behavior of particles in energy as being a artifact of the wave of the probabilistic nature of these particles. The fact that we could only describe particles in terms of probability distributions. If we start talking about superpositions of these distributions where we have multiple particles interacting, well, mathematically, you're going to get sines and cosines coming out as the result of the intensity patterns you're going to see. And so you can think of this as not being wave behavior, but being a probabilistic behavior. And that's how scientists, physicists, tend to think about reality. Not that particles are really waves, it's just that this is a manifestation of the inherent uncertainty in the nature of matter and energy. And it was to this point, the idea that there is not a determinacy, in that you can't say this electron, given this velocity, this direction, is going to end up here after some sort of interaction. We cannot say that. We can only talk about the probability of it ending up one place or another, or being detected at one instant or another, or being found when we make a measurement to have a certain energy. In that it turns out that all these quantities are fuzzy. They are not determined in advance. They cannot be determined in advance. And it was this lack of an underlying determinacy that bothered quite a few people back then, including Einstein. In fact, he is very famous for the quote, "I am sure that he does not play dice with the universe," referring to, most people think he's referring to God, and that the idea that we should have a determinate reality, in that, determinism, as started by Descartes, well, actually not started, but certainly popularized by Descartes. I don't think I want to go into philosophy that much. That's kind of getting far afield. But this was a concern of scientists back then, and Einstein turned out to be in a minority. And it looks like, we've been over 100 years since what we call the miraculous year, which was 1905, when we had 4 publications by Einstein that really kind of shook the planet. It's been over 100 years, and it's looking more and more like uncertainty is a fact of reality, and that there is not an underlying determinacy to things. So a lot of things to chew on philosophically, but the mathematics are incredibly precise in how they're linked, And because we've advanced in this mathematics, we have been able to explain a wide range of phenomena and predict new things to an incredibly high degree of precision. And so pretty much all the scientific advances in physics over the last 100 years have built on this. And it's considered, this whole quantum mechanics is considered one of the most successful theories mankind has ever come up with in its predictive power, and how well it's explained things and predicted things. Well, I'd like to pause now and go to a question on the slides. So since there's nobody in the classroom, we can just pull up that and not worry about turning on a projector. So,
Let me go back.
it's that one. Nope. What's the one? It was the one before that. Yes, we did that one yesterday. So yes, consider this question. If the uncertainty in the position of a particle increases, basically you know less about where it could be. Well, I've got a whole bunch of statements here, and only one of them is correct. Is only the uncertainty of its energy increased? B, only the uncertainty of its energy is decreased? C, only the uncertainty of its momentum is increased? Or D, only the uncertainty of its momentum is decreased? Or E, uncertainty of its energy and uncertainty of its momentum are both increased? Or F, uncertainty of its energy and its momentum are both decreased? Or G, uncertainty and energy is increased and that a momentum is decreased? Or the last one, H, uncertainty and energy is decreased and uncertainty and momentum is increased. So basically asking about uncertainty in energy and uncertainty in momentum, given that the uncertainty in position increases. Basically, this is all the logical possibilities, except that I didn't put in neither is increased or decreased. They both don't change, but that's not what's going on. One or both of them are going to change. And so that's the question. Consider the uncertainty in energy, consider the uncertainty in momentum, and do they increase, decrease, or stay the same? I'd like everybody to think about this. And if you've got notes on what I had up on the blackboard, that would be helpful to refer to those. So think about this for a bit, please. Okay, folks, that's enough time. Go ahead and hit a letter on chat, A through H, of what you think is going on here.
It's like 1H, 1G so far.
And a bunch of, I see some Ds.
Yeah,
So D, G, H, anything else?
not that I
No.
see.
Okay, could you pull that away so I can see what the questions are again? Okay, so we have defenders for points D, G, and H. Could I get a volunteer to defend, say, D, that only the uncertainty in the momentum is decreased?
I can try and explain.
Please do.
So going off
Yeah.
the stuff on the board, so the position and momentum are linked so that when there's an increase in one, there's a decrease in the other. So if the uncertainty for the position increases and the uncertainty for the momentum decreases, and the energy and time are also correlated, but in a completely different equation that I don't think the position really affects.
Okay. Could I get a volunteer to defend, let's see, we had G.
Yeah.
Could I get a volunteer to defend G? The uncertainty in energy is increased and uncertainty in momentum is decreased. So basically G is the same, agrees with D, but also has the additional idea that energy, uncertainty in energy is increased. Can someone defend that?
I'll go for G. So I believe just since the question's asking for the uncertainty in the position of the particle increasing, I would believe something needs to increase since its position of uncertainty is increasing. So I figured energy is a good thing to increase because obviously momentum is decreasing.
Okay, so you agree that increase in uncertainty in position will cause a decrease in uncertainty in momentum, but what was that about energy again?
I just believe since there's an uncertainty in the position of the particle that is increasing, that should reflect on its energy, which would make it also increase.
Okay, so there should be a correlation then between energy, uncertainty in energy and uncertainty in position.
Yes.
Okay, can I volunteer to defend H that the uncertainty in momentum is actually increased, and accompanying that is an increase, is a decrease in the uncertainty in energy. So this is like the opposite of G.
The guy who typed H actually meant G.
Oh,
Yeah, he just typed in.
okay, so Mr. Harris had chosen H. Was that the only person who chose H?
Yes.
Okay, and he said he mistyped and he really meant G. So we only have really two defenders here. So can we flip back to the camera on the board just a little bit?
Yep.
Okay, so yes, we have the uncertainty relationship between momentum and energy. The more we know about momentum, the less we know about position, and the more we know about position, the less we know about momentum. So those two are definitely linked. And we also have a similar relationship between energy and time. So I guess the discussion should focus, and everybody seems to agree about if we have an increase, is that how it was raised? Increase in uncertainty in position?
Yes.
That would give us a decrease in uncertainty in momentum. So the question is, does that affect energy and time? Actually, we're not really concerned about time, only energy. Is there a linkage between either momentum and energy or position and energy? That's what we need to discuss. Okay, let's go back to the slides. I'd like everybody to think about this and maybe exchange some chats or just take turns speaking through the microphone. What do you think's going on here? Is there a connection? And if so, which way does it go?
Yeah, I think just based on the lecture that they're inversely related. So if one is increased, the other would be decreased, especially when you were talking about having precise probability. The more we know about one, the less we know about the other.
That was Ms. Scheiss.
Yes.
Someone else want to speak up too, please?
So if one is we know that momentum's decreasing, it doesn't necessarily mean that energy is increasing. It just means we know less about it.
That's right.
Okay.
It's about uncertainties. Basically, think of like the standard deviation of what we'd expect to see. That's what we're talking about, not the actual energy, not the actual momentum. We're talking about the uncertainty. Think of it as like if we're describing all of these quantities in terms of a bell curve, what's happening to the standard deviation of those bell curves? We're not talking about what the mean is.
Okay, that makes sense. Yeah, I still believe that G is the more correct answer just because if one is decreasing, one has to be increasing.
But with you said if one is decreasing, the other has to be increasing. We already know which one is increasing. It's the uncertainty in position.
Yes, and that means the uncertainty of momentum is definitely going to decrease. The question is, do we also see a change in the uncertainty in energy? Basically, if we know more about momentum, do we know more or less about the energy? That's another way of thinking about it. Anyone else want to pitch in on this? Okay, if not, anything on chat? Any other comments on chat?
No.
Okay, go ahead and hit a chat letter to indicate what you're thinking of now. What's it look like?
Mostly D still, but the same people still chose, or if we have an additional G, it looks like.
So how many G's total?
2.
Okay, so it looks like most everybody is choosing D, but we still have a few people choosing G. Well, again, science is not a democracy, and none of you are right. The correct answer here is F. So everybody is agreement that the uncertainty of momentum is decreased, but since energy is related to momentum, in fact, energy is proportional to the momentum squared, the more we know about the momentum, the more we know about energy as well. Can we switch back to the blackboard? Yes, the relationship I'm pointing to is right here. Energy is equal to P squared over 2M. In fact, beyond the introductory level, most physicists refer to kinetic energy as P squared over 2M rather than 1/2 mv squared. So momentum is what's important here. And if we know more and more about momentum, the more we also know about its kinetic energy. And yes, there's an uncertainty relationship between energy and time, but this would also mean that as the uncertainty in position increases, so does the uncertainty in the time of, let's say, of its arrival. So think of this as a particle that's moving, and we're going to detect it someplace. If we know less about where it is, but we know a lot about its momentum and therefore its speed, well, we're not going to have a good idea of when it's going to arrive, say up in Idaho Falls. Does that make sense? So as momentum, as the uncertainty in position increases, we get an increase in the uncertainty in time and a decrease in the uncertainty in energy. So F was the correct answer there because we have that relationship between energy and momentum. But I could also make a similar relationship between an argument for the relationship between the uncertainty in position and the uncertainty in time. Basically, say time of arrival, if it's moving. Does that make sense to folks? Please unmute and say something, or maybe give me a thumbs up on the chat bar.
Yeah, that makes sense.
Any questions on this point? Okay, let's go to the next slide. I've got another question for you. So this is sort of related. An electron and a proton are accelerated through the same electric potential difference. Now, electrons and protons have the same magnitude of the electric charge. Remember that. But they do have different masses. And if we accelerate them to the same potential difference, what does that mean about the energies of the particles and their wavelength? That's the question. So you want to be able to refer to the de Broglie wavelength for a particle, but also think about what this means about the energy. So I got 5 statements here. So which has more energy, which has a larger wavelength? So in A, electron has more energy and the shorter wavelength. Or B, proton has more energy and the shorter wavelength. Or C, they both have the same energy, but the electron has the shorter wavelength. Or D, they have the same energy and the proton has the shorter wavelength. Or E, they both have the same energy and wavelength. So it's all the question about the wavelength of these two particles and their energy. If they're accelerated through the same voltage, the same number of volts, say 100 volts each, how will their energies, their kinetic energies compare after being accelerated through that difference? And how will their wavelengths compare? I'd like you to think on this a little bit, and you need to refer to those equations. The de Broglie wavelength, and also perhaps the idea of what kinetic energy is. Colton, if you're bored, you can pick up folders. Okay, folks, that's probably enough time to think about this. Go ahead and hit a letter on chat, please.
A, E, B, with A being most predominant. So far.
No B's or C's?
No B's or C's.
And we have some E's there?
We have 1 E.
Okay.
1 B. Rest are A's. Oh, 2 E's.
Okay. Okay, folks, we have people choosing A, D, or E. Nobody chose B or C. Is that right?
That's correct.
Can I get a volunteer to defend why A is correct? And the electron should have more energy and should also have a shorter wavelength. Go ahead and unmute and just speak up. Didn't we have more people choose A than anything else?
Yes.
So A is the most popular response, folks. So please, somebody speak up and defend it.
I was trying to give somebody else a chance to go. But I chose A because if they're both going through the same potential difference in kinetic energy, the electron would have more energy than the proton, and that would that would say that it would have a shorter wavelength. More energy is equivalent to a shorter wavelength, like in UV versus like a gamma ray. And I didn't think C, D, and E were right because I didn't think they could both have the same energy because they had different masses. So anyway, I eliminated C, D, and E for those reasons.
Okay, so the electron should get more energy because it has less mass, was kind of the reasoning. And if something has more energy, it's going to have a shorter wavelength. So did I sum that up okay?
Yeah, that's perfect.
Okay, could I get a volunteer to defend D, that they have the same energy, but the proton has a shorter wavelength?
Only one person chose D.
Mr. Case, I'm going to pick on you. Do you want to speak up and explain why you chose D?
Sure. So I think what I was thinking, as far as the energy, I'm still a little confused on how that works, but with the proton having the shorter wavelength, I think I was thinking like because it has greater mass, it would be affected less by the same energy. And so I just assumed it would have a shorter wavelength. That's kind of what I was thinking.
Okay, so same voltage should mean same energy, but since the proton has more mass, that's going to give it the shorter wavelength.
That's right.
Okay, could I get a volunteer to defend E, that they have the same energy and wavelength?
I don't really understand what it means by potential difference, but basically my understanding is that with most things with electrons and protons, they tend to have equal but opposite reactions to things, so it made sense to me that they would have the same energy and wavelength.
Okay, so the same voltage should mean the same energy, and the same energy should mean the same wavelength. Well, I'm going to, before we break up into discussion, I'm going to provide a few things that might help. Think of it as a clue. What is voltage? And if you look at the units of volts, the units of volts is energy per charge. So remember we talked about, since we had two flavors of the electric interaction, positive and negative, it didn't make as much sense to talk about potential energy so much as opposed to potential energy per charge. So that what's a high potential energy for a positive charge would be a low potential energy for a negative charge. But if we just look at the ratio of the potential energy per charge, that's going to be the same for both. So that's why in electricity, we talk a lot in terms of voltage rather than potential energy, because voltage is potential energy per charge, and that's going to be the same regardless of what charge is experiencing the electric fields that give us that voltage. So if you have some particle exposed to a potential difference, electrons are going to go one direction while the protons are going to go the other direction, because one will go in the direction of the electric field and the other one will go in the opposite of the direction of the electric field. But we're talking about the same magnitude of potential difference for both. So, and also think in terms of what that would mean for wavelength. Remember, wavelength depends on the momentum of a particle with the Broglie wavelength. The more momentum you have, the shorter wavelength you're going to get. So ponder that for just a minute, and then I'll ask for another chat punching. Letter punching, letter choice. Commitment, that's what it is. I have a fear of commitment. Okay, go ahead and hit a letter on chat. Do commit to something. What are we seeing? Any B's or C's?
One C now.
Now we have a C.
Yeah, we have three E's. Yeah.
And how many A's?
4.
Okay, so 4 A's. How many C's?
1.
1 C. How many D's?
No D's.
No D's at all?
No Ds.
Okay, how about E?
Three.
Okay,
3 E's.
okay, let's go ahead and go to the blackboard. So the energy that these guys will have, their kinetic energy, will be the charge times the potential difference. Basically, voltage is joules per coulomb. Multiply that by coulombs, you get joules. So since both the electron and the proton have the same magnitude of the charge, they're going to have the same energy. We're just going to see one particle going to the right and the other particle going to the left, but they're going to have the same exact kinetic energy. Now the question is, what is that? Well, that means that they've got the same energy. So I can't remember what the possibilities were. Yeah, so knowing that they have the same energy, that means C, D, or E are the correct possibilities. A and B are out. But let's look at momentum. If they have the same kinetic energy, if I could zoom over here, that means their momentum squared divided by their mass is going to be the same. And the two particles have different masses. So can someone tell me which particle, if they have the same energy, will have the larger momentum? Can someone tell me that? If both particles, the electron and the proton, have the same energy, which is p squared over 2m, which will have the larger momentum?
Proton?
That's right, because the mass is larger. So to keep this ratio the same, for a larger mass, you have to increase the momentum. Who is that?
Typecase typed it, and I'm not sure who spoke up.
Yeah, who just spoke up?
Crystal Shees.
Okay. So if the proton has the larger momentum, that means it has a shorter wavelength. So that means D was, is that right, D? Yes, D is the correct answer here. So this was a bit of a tricky one. But that's the result. Now, I'd like to kind of move on to discuss, and just to be clear, we've now finished pretty much all the material that's going to be on the exam on Friday. And as a recap, the exam will be here in person. If you have not contacted me to make other arrangements, you've got to do so immediately, because I have to make arrangements days in advance for proctors. And also, we have to make arrangements in advance for the proctors to set up Zoom sessions for these exam sessions. So there's a lot of stuff that has to be done if you can't be present. And if you haven't contacted me, you've got to do that immediately. And so you'll be here in person. We're going to use 132 as a overflow room. Again, you'll have that equation sheet, and I made some minor corrections to it a couple of days ago, basically removing a typo. The equation sheet that's on the webpage is what's going to be provided during the exam. And something I hope to have by the end of the day is an online version of the practice test for exam 3. And you'd have to use this online proctoring service for it. And since that's the system we're going to be using for the final exam, I strongly encourage everybody to try the practice exam for both the final, which I hope to get up probably this next weekend, but also the practice exam for exam 3. I strongly encourage all of you to give that a try, because it, again, involves using a Chrome browser and downloading special software. So it's critical to give this a couple of tries to make sure you are not going to have hiccups or problems with the actual final exam. after Thanksgiving. So do look to that and give that a try. And gosh, we have less than a minute left in class, and I know I've gone over on occasion, so I think I'll just end it here. Thank you for your attention, and I hope to see folks then on Wednesday, and I hope to see all of you on Friday.